Hello everyone, welcome to the Electronics with Bill channel. I'm a retired engineer and after that I taught electronics at the University of Texas Arlington for about 6 years and so I'm not doing that right at the moment, so if I just do some videos on electronics for those of you that are interested. And for today's video, let's look at LTspice, an extremely useful tool. It's free, and I would suggest that you you have LTspice in your toolbox, so to speak, if you're an electronics hobbyist, and even if you're a professional engineer. Although if you're an RF person, you probably would want a tool more oriented to transmission lines and S parameters. But for many things, LTspice is extremely useful. So, what are we going to talk about today? Let's talk about how to get started in LTspice, where to get it, uh, uh, and uh, and then how to enter some schematics, simple things. And then we're going to model an amplifier, do an AC analysis, frequency response on an amplifier, and also on a transformer, build a transformer out of two inductors and couple them, make a transformer. And then let's do that same amplifier in the time domain, transient response, and also then look at the pulse response of a RL circuit. Now, there's one thing that doesn't work too well with this particular screen recorder that I'm using, and that is some of the pop-ups don't get they won't show up. You won't be able to see the pop-ups that I see when I click on things. So I'm going to have to tell you what I see, um, and I don't think that will be super limiting, but it's not great. Uh, I can try to move the pop-ups right in the center of the window, and they don't even get recorded. Other than using the different editing tool, I'm not sure what to do about that just yet. So anyway, let's get started. And for the first little segment. Hello, everyone. Let's talk about LTspice here. And I guess the first question you have is, where do you get it? LTspice, I would suggest, but there's more than one way. I would suggest just www.analog.com. That's Analog Devices web page. And then under that, select the design resources. I believe that's right at the top. And then resource library, and then design tools and calculators, and then finally LTspice. And then you download it. And I would suggest using Windows. Macs do work. It's a little harder to make it work, but they do work. No question about that. I've seen it done. So, but I'd suggest Windows. And so there you go. So once you get it downloaded, and then it'll want to do some updates and stuff like that. And so then what would you do? File, new schematic. File, new schematic. I don't know if you can see this pop up or not, but that's kind of fairly straightforward, and it'll open a blank page, and then you can start doing stuff like, for instance, I hit edit text, which I don't know if you can see that pop up, that comes up when you click edit, but there's one that does pop up, and then I put this in just as text. That's where that came from. Now, then you can add your schematic. Now for our first segment on the AC analysis of an amplifier and on a transformer. Now let's get started. Okay, let's look at the schematic of this amplifier. And let's see. All right, so we have a single stage amplifier built with a 23904 BJT, and we're driving it from a sinusoidal source for our AC analysis to start with. And so let's just see how you would enter this stuff. Some of these things are not completely trivial, but I think it's fairly straightforward. So firstly, how do you delete things? Because we're going to be needing to delete some stuff here. For instance, if you hit your delete key on your keyboard, you get a little pair of scissors, and you can use it to cut wires and delete components and things. So I'll just cut some wires here, and we'll put them back in a minute. So you see, if I clicked on that component, it would go away, but I'm not going to do that. And so you can see that's how the delete works. Now, so now, by how do you enter things? Well, if you want to enter this supply right here, you come up to Edit, and then Components, and you cannot see this pop-up. There's a pop-up right now. You come down and select Component, and then there's another pop-up that appears, and you go over to the far right, the scroll bar at the bottom, over to the far right column, and select Voltage. And then in that pop-up window, you select Place, and then you will be able to place things like you see right there. And if I click it multiple times, I'll get multiple instances. I can click it as many times as I want. And while you're in the move mode, if you were wanting to place this one right here, you might do a Control R if you wish to rotate it, how it needs to be rotated. And then you can place still more if you want. So we don't need most of those. But now, what about the resistors and capacitors and things? Well, for resistors, you can come up right to the top of your screen. Resistors and capacitors and inductors, you come right up to the top of the screen and get R, C, and L, and ground. Your grounds, you need some grounds, so those are right at the top of the screen also. Or you can go to Edit Components. And there would be a way to place to select resistors and capacitors, and then you place them. So for instance, if I select a capacitor here, I come down here and I got a capacitor, and I can do a Control R if I wish to, and then I could place it there, except there's already one there, so I won't do that. And then likewise for the resistors, and grab a resistor here and place a bunch of resistors if I need to. And the thing that some people might have issue with maybe is the BJT. So where do you get that? So under Edit Components, if I edit, and that pop-up that you can't see, and you come down and select Component, and then you get another pop-up you can't see, and then go to NPN, and one of the third or fourth column, NPN, you click that, and then Place, and you will see an NPN transistor. You can place that, and multiple instances if you want, and of course, the Control R works if you need it, and the Control E to mirror it. So between the Control R and the Control E, you can orient that however you want to. And then the next thing you need to do is to right-click on it, and then in the pop-up window, which you can't see, you select Pick New Transistor, and then you select from a list 2N3904 is what I'm going to select, and then from this point on, that device is a 2N3904, which I could use to replace this one if I wish to. So now I'm going to go get my scissors out, and we're just going to delete all this junk that we made here. You can't run a sim with a lot of floating nodes. It'll crash on you. So you have to at least partially wire some of this stuff up into something if you want to run it. If you want to run it and have it run. Now let's fix our wiring. So I selected the wire tool up here, this one, and we're just gonna left click here, left click, about pretty straightforward, I think. Left click here, then left click, and then left click, and so I fixed the wiring, and now we're ready to go, except for the two sources. So this guy, if I right click on him, I get a pop-up, and basically I can enter a DC value as 10 volts, and when I do, I can change that to 8, for instance, and then it'd be an 8-volt source, but I'm going to go back to 10 again. And so that's pretty straightforward, I think. Now it's a little bit trickier over here for the AC source. We're going to right click on this, and for the AC analysis, you do not select a sign. You're going to select a sign for the transient analysis, but not for the AC analysis. For the AC analysis, all you need is at the right-hand side of this box here, AC amplitude 1, AC phase 0. And you select those two, and AC amplitude 1, AC phase 0, in two little places on the right-hand side of the box it appears, and then OK, and then you'll see this AC10 here by your source. This appears when you're doing the transient analysis. In fact, I'm just going to delete that for now, so it's not a distraction. So right now for the AC analysis, all you need is the AC10. Now I would think we are ready to configure our simulation. What do we want the Spice to do? Okay, so we're going to come up under Simulate, and we're going to come down to Configure Analysis. And then at the top, we have a choice of several different types of analyses that can be done: transient, AC, DC sweep, noise, DC transfer, DC operating point, and transient frequency response. All right, so we can, those are the choices. We're going to select the second one, AC analysis, and then in the relevant boxes that are blank, we select decade, DEC. Decade, that's going to give us a log response, frequency response. On the x-axis, it's going to be log frequency in decades. So as in 1, 10, 100,000, so on and so forth. 10 points per decade or more, if you wish. In fact, I'll make that 20 just for giggles. It doesn't have to be just 10. And then you're going to pick a start frequency, and I chose 1. That's 1 hertz, and the stop frequency of 100 MEG, MEG megahertz, 100 megahertz. So that's 8 full decades, and that's a super wide frequency range. And by the way, it's not 100 M, 100 MEG, MEG, or 100 E6 or 1 E8, but not 100 M, because that would be millihertz, and that won't be what you want. So we say OK, and now we've told Spice what we want to do. We've got our source configured, we've got our supply, and so when I click run here, Spice is going to do an operating point analysis on this to see how it's biased, and then it's going to run a small signal analysis. All right, and we will get what we want. So I'm going to run this, and I get my window here, and now I have to tell Spice what I want to see. So let's look here and see what's going on at the output of our source. So we have this is a 50 ohm source, a voltage source, and a series 50 ohm resistor, 50 ohm source. If I click here, I'll see the voltage on the input. And there we go, versus frequency from 1 hertz all the way to 100 megahertz. And in the mid-band region, I could read off pretty much on the left-hand side about a half a dB down, minus 0.5 dB. Now, if you want more accurate and not have to try to figure out, what this is reading off on the left axis over there, if you left-click on this, a dialog box will pop up over the right side of your screen, which you can't see again, which says that at 10 kilohertz, for instance, I'm minus 513 milladB, which means minus a half dB. So this voltage, this is 0 dB here. 1 volt is 0 dBV. This is minus a half a dBV. That's something around 0.95 volt, let's say. So this is not matched. In fact, this is a 50 ohm source driving approximately an 800 ohm load. So there's not too much drop across this resistor. If this was matched, and that was 50 ohms looking in here, this would be minus 6 dBV here, indicating this voltage would be half a volt. This voltage is now about 0.95 volt, just for your information. Now, what about over here? This is going to be our output. This is kind of what we want to see. This is our load, by the way, for this particular sim. There's no, we didn't cap couple to anything else. This is our load. Is this resistor right here is our load. And so if I click there, I see my output in red here. And by the way, that was blue. That's to start with, and blue is works really good for me, but it doesn't show up in the screen capture. So I changed it to red. And so what do we have on the output of the amplifier at 10 kilohertz? And that's 15.91 dB above a volt, which is about 6 volts, 6.5 volts, I think. Okay, how would you find out? How would you figure that out? If you undo the dB by dividing it by 10 and then raising 10 to that power, and then take the square root. All right, that's how you would undo the dB. And that was how you get this the roughly 6 volts there. Now, so what can we say? Well, what's our 3 dB frequencies here? Let's go. We're 15.9 dB in the mid band here, this big wide flat region here. So let's go down at the bottom end. We're looking for 12.9 dB, 3 dB less than 15.9 dB. So what frequency are we 12.9 dB on our output, dBV on our output? Now let's see. There's 13.9, 13.7, 12, 13.2, and 12.8. So this is a little bit low in free. This is a little bit low. We went a little bit too far. We were looking for 12.9. We got 12.78. Well, that's close enough for me. And that's about 17.78 hertz. That's what this says right here. So around 18 hertz is where we're 3 dB down on the low side. If you wanted to try to calculate that yourself, you could take this 10 microfarad capacitor in series and the 800 ohm impedance here. Actually, you use 850 ohms, this 50 plus that, and calculate the RC high pass corner frequency, and you'll get around 18 hertz, which is verified here by LTspice. All right, now, and this is AC analysis that we're doing. What about on the high side? Well, I can grab this cursor here and drag it over to where, try to get 12.9 dB on the high side. And that's our 13.26, 12.78. So I got the same problem here. I'm looking for 12.9 dB and I got 12.78. So I'm a little bit too high in frequency, and this is 70.8 megahertz. So it's 69 megahertz, I think, is the 3 dB frequency on the high side if you want to pick nits about it. All right. Now, there's nothing here in the schematic that would be indicative of what the higher 3 dB frequencies is. This would all be infinite bandwidth as far as what's showing here on the schematic. But of course, the device model has capacitors in it, which make the frequency response roll off at high frequencies. So that's what's going on there. I want to say something about this is based on the small signal model. But LTspice does not check to see that your input is truly small signal. So I could, if I wanted to, come over here and select, instead of AC amplitude of 1, 0, I could select AC amplitude of 100, 0. And now, see that AC 100, 0. So now I've got a 100 volt source here, which is ridiculous. And if I rerun the simulation, you see you get exactly the same frequency response, except that the output, instead of being 15.9 dB is in the mid-band. It's 56.9 dB, I believe, 55.9 dB. Okay, so it's 40 dB more than before, and instead of being 6.25 volts, it's like 625 volts. Again, this is ridiculous. It can't happen, and so you cannot use the AC analysis to predict linearity. But as you can see, you can get a super broadband frequency response picture almost instantly. And it's extremely useful for that purpose. You want to see what your frequency response is going to be. You're going to have to run a separate analysis in the transient, a separate transient analysis if you want to see where things clip and what the waveform looks like, that kind of thing. Now, what about next? That's really kind of what I wanted to show you on the amplifier here. Let's run the same AC analysis on a transformer, which we have to build, which we don't have to build because it's already built. But let's talk about this transformer, because a transformer is not obvious in LTspice. There's no, if you go under edit components, you won't find a transformer. Now, I just attached this to the same source so you can run both of these simulations. In fact, I've already simulated this. We just simulated it just now. But what are we looking at here? So we have this source, a 50 ohm resistor, and we want to build a transformer that transforms 50 ohms up to 5,000 ohms. So that's a 100 to 1 impedance transformation. 50 to 5,000, 100 times. What does it take to do that in the transformer? An ideal transformer takes a 10 to 1 turns ratio. So 10 to 1 turns ratio, if you're into transformers, with 1 turn here, 10 turns here, or the secondary has 10 times as many turns as the primary, that will give you a 10 to 1 voltage translation and a 1 to 10 current translation. So 1 volt here, 10 volts here. 1 milliamp here, 10 milliamps there. Constant power just changes the voltage current ratio. And when you go up by a factor of 10 in voltage and down by a factor of 10 in current, then voltage divided by current is 100 times higher on this side than on that side. So it all makes sense if you think about it a little bit. And if you have a 10 to 1 turns ratio, the inductance ratio between primary and secondary is 100 to 1. So the inductance ratio primary to secondary is the same as the impedance ratio. Now here we have a 10 millihenry, that's the M primary, and 100 times that on the secondary, which is 1 Henry. That's 100 times inductance ratio. And absent this command right here, if I delete that, I have a circuit that does absolutely nothing. I have 50 ohm resistor driving an inductor and another inductor connected to a resistor. That's going to do absolutely nothing. All right. So I have to tell Spice that I want these two inductors to be coupled. How do I do that? All right. So pay attention here because you won't see this box. Edit. Spice directive. Select that. It'll open up a little box and you're going to type what you see appear on the screen here in just a second. K, capital K, probably doesn't matter if it's capital or not, and then some number. I'm going to use 1. It's the only one in the schematic, so why not? And then the two inductors that you want to couple, L1 and L2. Those are the two inductors we want to couple. And then what do we want for a coupling coefficient? 1. Okay, this is an ideal transformer. I want to say something about that in just a minute. So I'm going to say OK here, and then I get this spice directive that I need to place in the schematic someplace. And as soon as I place this in the schematic, you see the dots that appear on these two inductors. That tells you that they're coupled to something. And this is the SPICE directive that tells how they're coupled. All right, so what does a coupling coefficient of 1 mean? It means there's no leakage inductance. It means that every turn on the primary couples to every other turn on the primary perfectly, and also to every turn on the secondary perfectly. And the reverse is also true. If there's a current flowing in the secondary, the flux is generated by that current in the one of the turns couples to every other turn and every turn on the primary. No flux leaks out that couples one turn, but not all the turns. Okay, that's what's meant by a coupling coefficient of 1. That's the best you can do. Coupling coefficient of 1. That's what transformer designers would desire. So this transformer is ideal in that respect. It has no loss. There's no resistance in the windings or anything like that. And the windings are tightly coupled, coupling coefficient equal to 1. What this is not ideal on is the inductances are not infinite. An ideal transformer would have huge inductances, and we will see that what that does in our frequency response. Because we don't have infinite inductance. We have a 10 millihenry primary and a 1 Henry secondary. So let's see what happens here. I'm going to delete this frequency response plot from the amplifier and run the simulation again, which reanalyzes the amplifier, but we don't care about that. And now let's look here at the transformer primary and at the transformer secondary. Okay, so we see our two responses. And you know what? I got to change this back to 1 here. I left it 100. Let's run this again real quick. Although the transformer will certainly work at any voltage. I mean, this is ideal. So I put 1,000,000 volts in here and get 10 million volts on the output. Even though you know that probably wouldn't be practical. So now I have 1 volt here. So there's 1 volt here. And what voltage do I have here? Well, let's look in the midband region here on the green plot. And so at 10 kilohertz, I've got minus 6 dBV. So the voltage here is minus 6 dBV. The phase is virtually 0. So that means that the impedance looking into this transformer is resistive because the phase is darn near 0 degrees, like would be for a resistor. Current voltage relationship is the current and voltage are in phase, meaning that it's resistive looking in here. And because of the fact that this voltage is half of that voltage, minus 6 dBV is half a volt, 0 dBV is 1 volt, that means that this is a matched interface. 50 ohm source driving 50 ohms. The voltage is half. Across the transformer primary here, half of what's here, because we drop equal across this 50 ohms and then the 50 ohm resistors that you see looking into the primary of the transformer. All right. So it's matched on the primary, and then you know it has to be matched on the secondary also, because this is all lossless, and you know, so if it's matched one place, it's matched every place. That's kind of one of the rules of circuit theory. Now, what voltage do we have on the secondary at that same frequency of 10 kilohertz? 14 dBV. So we got 14 dBV here, minus 6 dBV here, 14 dBV here. There's a 20 dB difference, and that is 10 to 1. 10 to 1 voltage multiplication. Another way of looking at it, minus half a volt here, 14 dBV is 5 volts. How do you know that? 20 dBV is 10 volts, and 6 dB less than that, 5 volts. All right, now you can take 14 and divide by 10 and raise 10 to that power, and then take the square root, and you'll get 5 also. All right, 5 volts here, half a volt here. There is our 10 to 1 transformer. 1 volt, 10 volts, 10 milliamps, 1 milliamp. 100 to 1 impedance translation built with um, two coupled inductors. The dots appear here when these two inductors are coupled. If I delete that coupling statement, those dots will go away. What do the dots mean? Dots are polarity. Basically, current into the dot on the primary results in current out of the dot on the secondary. Okay, so why do we have this rule about the current into the dot on one side is current out of the dot on the other side? Uh, and obviously that applies to primary or secondary. If the current's going into the dot on the secondary, it's coming out of the dot on the primary. Why do we have that rule? Well, it kind of makes sense if you think about from a energy conservation perspective. This transformer is a power conserving device. It doesn't generate power or absorb power, ideally at least. And so from the primary has to be acting as a load as far as this source is concerned. And so what do we know about loads? Well, the current has to enter the positive terminal of a load. That's one of the fundamental assumptions in our circuit theory. And then the source, however, the current exits the positive terminal of a source. And this secondary of the transformer is a source as far as this resistor is concerned. So current would be exiting the positive terminal of the primary when it's entering the positive terminal. I'm sorry, exiting the positive terminal of the secondary when it's entering the positive terminal of the primary. And that's the reason why we have this rule with the dots. Now, one last little thing here, frequency response. Remember, we said this transformer was ideal, except for we don't have infinite inductance. And we can see that effect here. If we go down to 1 kilohertz, that's about as low as we can go here with the 50 ohm source and load there, 50 ohm source, I mean. And then if we go less than that, we start to roll off, our frequency response starts to roll off. And why is that? Well, if you want to think of it this way, just consider we open circuit this to take the 5,000 ohm load off the secondary over here. And then what does a transformer look like when we completely unload the secondary? Well, it basically just looks like its primary inductance. And I think you can kind of see that without even doing any math, that if we go low enough in frequency, this reactance to this primary inductance keeps getting lower and lower and lower, and eventually all of our source voltage will be dropped across this 50 ohm resistor, and there won't be anything across the primary to couple over to the secondary. So that's why our frequency response rolls off at low frequencies, because we don't have these inductors big enough. And so if we wanted to extend this down to 100 hertz instead of to a kilohertz, well, we could make both of these inductances 10 times as big. And then if you wanted to go lower than that, you make them still bigger. And then maybe you can appreciate why 60 hertz transformers are so big, because they need big inductances. Because we're working at 60 hertz, right? So pretty low frequency. So that is it for this transformer. Okay, so that completed what I intended to show you on the AC analysis. And of course, there's a lot more but that'd probably be enough to get you started at least. And then let's do a little time domain analysis now. So what we're going to do is look at that same amplifier in the time domain, or in a transient analysis with a sinusoidal source. And then I wanted to show you a pulse source on LR low pass filter, just as to kind of demonstrate using the pulse source and the time domain response of the LR low pass filter. So that let's get started on that, and then I will probably finish up this video. All right, so let's look back at the same amplifier circuit, only in the time domain now. Now, the last analysis that we did, we looked at its frequency response over 8 decades. Now we're going to do a single frequency analysis in the time domain and see how we do that. Okay, so we have our amplifier entered. It's going to be the same one as last time, and no changes there. Only thing is now we have to configure our source. And so I'm right clicking on the source, and then on the left hand side I'm going to select sine, and then that opens up about 7 boxes wanting different things. First is a DC offset. I'm going to leave that blank. Next is an amplitude. I'm going to select 0.5 volt, 0.5 volt. A frequency, let's say 100 kilohertz, 100K. Time delay, leave that blank. Theta, 1 over S, leave that blank. A phase, leave that blank. Number of cycles, you could put in a number of cycles if you want, but if you don't, it'll just run for the length of the simulation, and that's fine. So basically, the only 2 parameters I entered was the amplitude and the frequency. If I say OK, then this appears, and that's relevant to the transient response, which we haven't requested yet. The only thing we've requested right now is the AC analysis. So let's request a transient analysis. So how about simulate up here, configure analysis, and now we're going to select the very first simulation type on the top, which is transient. You can't see this pop up, I apologize. And we are running at 100 kilohertz. So I set a simulation time, a total simulation time of 1 millisecond. That would be 100 cycles. And then told LTspice to start saving data at 0.9 of a millisecond. So basically, I didn't need to enter that second command, but that second input, but this will just save me magnifying the response to avoid having a bunch of cycles all crammed together real close. So if I say OK, you'll see the .tran command here. Now if I move that down, see how it appears on the screen. So .tran, there's our, and then the simulation ends at 1 millisecond, and it starts saving data at 0.9 of a millisecond. So basically only 1/10 of a millisecond will show on the screen. And that's pretty much all there is. We're ready to run, and if we do so, we can see that our output here should be sinusoidal, and it is, and it's you can see exactly what the waveform looks like and what the voltage swing is, and what the peak, what the maximum and the minimum are. And I think you can see here that since we're up about our peak here is, again, in the little dialog box, which you can't see, peak voltage is 9.3. So we only have 0.7 of a volt before we get to our supply rail, and we're kind of close to clipping, but we're not clipping. So if I raise this to 0.7 volts, and then I can edit the command right there on the schematic. I don't have to open up the simulation dialog box again, but I could. So now if I run the simulation again, that'll be with a 0.7 of volt amplitude. By the way, that's 1.4 volts peak to peak on the input, 0.7 volt amplitude. That's what that means. And now I think you can see that we are flat topping on the top. It's not super obvious we're clipping, but if you look, the waveform is flatter on the top than it is on the bottom, and we are right at 10 volts on the peak, 9.97 volts. So we are clipping right now, but it's not grossly obvious. And if you want to see grossly obvious, let's up this to like 0.9 volts, and then we'll be clipping, obviously. So you can see the advantages and disadvantages of the transient sim is if you wanted to know frequency response, man, you'd be there for a long time because you got to run a separate sim at every frequency. And then if you want to know what it does for different amplitudes, you got to run it at all the different amplitudes. So here we go at 0.9 volt now. And I think you see we are clipping on the top and on the bottom. And again, we show only 10 only 100 microseconds of time here because we're only showing the last 0.1 millisecond of our sim. All right, so we only have 10 cycles showing here versus we would have 100 cycles showing if I had left that off, that 0.9 m off on our transient command. Now we can do that. I can show you that if I just leave that off. I'll run the sim again and just so you know, just put a stop time. That's all, and then you know that's okay. You just get a real kind of a busy screen there, and if you want to see what it looks like in closer detail, you can magnify it if you want, like this. Oh, hey, pay your money, take your choice. Or you could settle. You could just run a shorter sim time and get pretty much the same result. The advantage of that "don't show me data until a certain time" is if suppose there's a length of time where there's a transient response that hasn't rung out yet, and it makes the data invalid at the beginning of the simulation. So you have to run a fairly long simulation to let that transient response settle out, and then you've got a million cycles showing, and so this has a big advantage in that you can say, hey, let it start it and let it run for a while, and then start showing me data, and it's very useful, I think, in some cases, and you would realize that on your own if you were doing this. So I think that's about all that needs to be said about the transient response. You have to set up your source as a sinusoidal source for this type of response, and then and you have to change the amplitude if you want to see what it does at different amplitudes, and you have to change the frequency if you want to see what it does at different frequencies. And there's none of this 8 decades of frequency response plot in 2 seconds. Okay, so the advantages and disadvantages of each. All right, so that's it for the amplifier. Now let's look at another circuit, which would be, I'm going to open up a different schematic. I'll open. And it's going to be a very simple circuit. Close that. Changes. No. Okay, so here we have LR, low pass filter. Now, I don't know, some of you may not have ever thought about that. Most of the time people use a Series R shunt C for a low pass filter, but this is also a low pass filter. And so it has a transient response, as does the RC low pass filter. And it turns out that in some ways it's identical. So how would you show that? Well, you need to be able to provide a pulse input, and so you can see how the circuit charges and how it discharges, applying RC terms to LR. And so as it happens, the current in the LR circuit looks, the math is identical for the voltage in a series R shunt C circuit. Now here's what it is. I of t, current as a function of time, current flowing around the loop here, is the max current times 1 minus e to the power minus t over t0, where t0, instead of being RC, is L over R. Of course, there's the L and there's the R. And that's what the I looks like. And in this special case right here, because of the fact that this R is 1 ohm, the V here across the R is also equal to the I. So this would also be V of t in this special case. And this V over R here, that's the maximum current. Well, I think that might be obvious by intuition that if I turn on this source and leave it for a long time, eventually all of the source voltage appears across this resistor, and the current that's flowing would be this voltage divided by that resistance. Hence, that first term there, V over R. All right, so, and as that happens, this is 1 volt and 1 ohm, so V over R is 1 for this circuit. And L over R, which is our time constant, is 7 millihenries divided by 1 ohm, or 7 milliseconds. That's our time constant for this circuit. Now, we have to set up our transient response. So, as in the amplifier case, how do you do that? Well, you come up here, simulate, configure analysis. The pop-up that you can't see is at the top. One of the top left choice is transient. So you click that, and all you need to enter is the stop time. Okay, I could enter a time to start saving data, but I didn't. I just entered a stop time. 0.41 seconds is what I entered, and hence this is what you end up pasting in your schematic. This is a SPICE directive. You need to, after you select the things that we just talked about, you need to paste this into your schematic with your left mouse button. Now this, it comes from configuration of the source. Okay, so you right click on the source, and in the dialog box you're going to see 1, 2, 3, 4, 5, 6, 7, 8 things that you can fill out. And then after you do that, this right here will be populated. So what's our initial voltage? 0, 0. What's our on-state voltage? 1. What's the delay between the initial and the ramp up to the on-state? 0. So in other words, we want to start ramping up to the on-state immediately as soon as at the beginning of the pulse time. 0 delay. What's our rise and fall time? 1 nanosecond for this particular simulation. LTspice has a problem if you use 0 rise and fall time, and I think it makes the simulation have to have this infinitely short step time, and it just basically doesn't converge well. And there's no reason to have a femtosecond rise times in this simulation. Here, 1 nanosecond is just as good as 0 for this simulation purposes. You'll never know the difference. So anyway, that's where these came from. And then how much time do we want to spend in our on state with the voltage 1? 50 milliseconds. And what's the period of the whole pulse? 200 milliseconds. So it's 25% duty cycle. It's on a quarter of the time, off 3/4 of the time. 200 millisecond total period, and 3 cycles. All right, so in our simulation time, we will have 2 full pulses, and there'll be a little bit of the third pulse before our simulation timer runs out here. Now, that's designer's choice, and there's no reason that needs to be 0.41. It could be 0.21, and just look at the first pulse, or you can have more showing. You'll see in just a second. No big deal. Anyway, okay. And then if you didn't have this populated, that would become populated. If I don't, for instance, if I turn this off, See, I'm hesitant to do that, but if I turn this off, well, you don't see that anymore. If I go back to advanced and turn on pulse, then I have to redo it all, so that's my bad. But anyway, 0, 1, 0, 1 nano, 1 nano, 50 M, 200 M, and 3. Okay, so there we go. There's what we had before, and you can move that if you want over here, so it doesn't interfere with other things. Doesn't matter in the sim, but it just makes it harder to read things sometimes if you got that text all over something else. So alrighty, so then we're ready to go, and so let's run this and we'll see what happens. All right, and taking its sweet time for some reason. And the so let's look here. I would suggest when you configure a pulse like this, you look at it first just to make sure that it's what you thought it was supposed to be, that what you get is what you were expecting. And so what do you see here? You see a pulse that at t equals 0 appears to ramp up from 0 volts to 1 volt. Actually, there's a 1 nanosecond rise time, but you can't even begin to realize that in this particular picture on the scale. And then it stays high for 50 milliseconds and then ramps back down to 0 volts in what appears to be 0 time, but it's really 1 nanosecond. And then at the end of 200 milliseconds, we have our second pulse. And then at the end of 400 milliseconds, we have the onset of our third pulse, and we don't get to finish that because our simulation timer runs out. So that's what we expected, and that's pretty much, makes sense. Now what you would more likely to care about is what does the voltage here look like, and then we see what would look identical to the RC, the voltage on the capacitor, if that was an RC there. Okay, and this would this is actually kind of a current waveform, but it turns out to be a voltage waveform also because this is a 1 ohm resistor and we're looking at the voltage across the resistor. Alrighty. So basically that kind of concludes what I wanted to show you about the pulse response for a low pass filter that you might not have been familiar with. It's a one pole low pass filter, as is the RC. Only thing, this is an LR, and basically the if you're an RF kind of person, you would be working with the low pass filters that have both inductors and capacitors. Inductors in series, capacitors in shunt, and this is an example of just one inductor in series. So that will conclude this segment on the pulse setup for LTspice. Thank you for watching, everyone, and I hope you were able to get something out of this video. And we covered a couple of cases, AC analysis, one on an amplifier, frequency response, and the other on a transformer, to demonstrate how to make a transformer not intuitively obvious in LTspice. And transformers, sometimes you actually need one. Other times they're useful as placeholders if you're not quite sure how to do an impedance translation, and you can implement an ideal transformer and get the job done, and then figure out how to do it later, how you're actually going to implement it, the impedance translation. But in any event, we did cover that, the transformer, and then also in the time domain, how to model a sinusoidal source and a pulse source for an amplifier and a low pass filter. So um, that note, I think we can terminate this video. It's kind of long, but thank you for sticking with me, and please don't hesitate to comment. I like them all, positive or negative. Negative might even be more useful than positive. So anyway, we'll see you in the next one.